Here we are, section 2.5. We're continuing on looking at term theorem, a true statement that follows as a result of other true statements. Okay, so it's kind of like a postulate. It's a rule that we use for geometry. The main difference is postulates are just accepted because they're usually kind of common sense. The theorem is a little more complicated idea or rule, and so it has to be proven to make sure that it works in all cases. So, two-column proof. We have numbered statements and reasons that show the logical order of an argument. All right, we kind of touched on this in 2.4. We just didn't identify it as a proof, and we didn't number all the statements and reasons. But in order for it to be truly called a proof, it's got to have each statement and reason numbered. And we're just showing the logical order of an argument, one step after another, that explains why something is the way it is. All right, so theorem 2.1, properties of segment congruence. Segment congruence is reflexive, symmetric, and transitive. All right, we've already touched on these properties a couple times in the past, but now we're looking at them as far as how they relate to segment congruence. And so reflexive property is just going to say that for any segment AB is congruent to segment AB. So any segment being congruent to itself is the reflexive property. Symmetric property says if segment AB is congruent to segment CD, then segment CD is congruent to segment AB. It just doesn't matter which side of the congruent symbol it is. If they're congruent, they're congruent. And the transitive property of segment congruence, if segment AB is congruent to segment CD and segment CD is congruent to segment EF, then segment AB is congruent to segment EF. Right? So segment AB and EF both being congruent to CD means that they should be congruent to each other. All right, so here we have a proof we want to do. It says given the length of EF equals the length of GH, prove that EG is congruent to FH. Right, and that should actually have little segment markers over those. Segment EG and segment FH. Since we have a congruence there, we need to write them as segments, not as lengths. All right, so I want to prove that from E to G, that segment is the same as from F to H. And so we start off any proof on the left side. We're going to have the statements and the reasons why those statements are true on the right. And the first statement is always the information they give us, which they gave us that EF is equal to GH. And our reason for that is it was given to us. Right? It's the given. All right, so now we need to work from there to proving that segment EG and segment FH are congruent. So EF and GH, those are the same length. And if I look at EG and FH, really what we're doing to make those two bigger segments is we're taking the EF that they gave us and we're adding FG to it. And we're taking the GH that they gave us on the other side and adding FG to it so that we get EG and FH. So we're going to bring in FG into this by saying that FG equals FG. The length of FG is equal to the length of FG. Anytime we say something is equal to itself or congruent to itself, that is the reflexive property. And we're using an equal sign here, so we're going to say the reflexive property of equality. Okay. So, and then just like I said, in order to get EG and FH, we've got to take EF and GH and add FG to them. So I'm going to take this equation here, and I'm going to add FG to both sides. Right, so EF plus FG is going to equal GH plus FG. And so we're adding the same thing to both sides. So that is the addition property of equality. And then, so now we know when we look at it, or we should be able to look at it and see that when we take EF and add FG to it, that gives us FG. And when we take the GH and add FG to it, that gives us FH. But we need to state that in this proof that that is a fact. All right, so I'm going to come back here to 4 and say EG is equal to EF plus FG. And also FH is equal to GH plus FG. And so what we're doing is we're saying that one bigger segment, EG, is made up of two smaller segments added together, EF and FG. Same thing with FH. It's a big segment made up of two smaller segments added together. And so the reason we can give that we know that is true is called the segment addition postulate. All right, so now we know that EF plus FG is equal to GH plus FG. EF plus FG is the same thing as EG. And GH plus FG is the same thing as FH. So I can replace EF plus FG with EG and GH plus FG with FH. And that'll give me that EG is equal to FH. And to get that, we substituted. All right, so right now it looks kind of like we're where we need to be, except for we have an equal sign here and we have a congruent sign, what we're trying to prove. So I do know, however, that if two segment lengths are the same, then the segments themselves are going to be congruent to each other. So we can switch, say segment EG is congruent to segment FH based on the fact that their segment lengths were the same. And the reason we will use there is definition of congruent segments. All right, so anytime we need to switch between two segments being congruent or equal, this is basically the rule we can use, definition of congruent segments, and that works if we're going from congruent to equal or equal to congruent. All right, so that finishes that proof. All right, next one, we're going to complete the proof, and they give us quite a bit of information, given that segment RT is congruent to segment WY, length of ST is equal to the length of WX, prove that segment RS is congruent to segment XY. So ultimately, we want to prove that RS from here to here is the same as X to Y here, which are on two different segments, but there are some things that are related there between those. So first off, just filling in the missing parts. So we need a given. So there are two parts to the given. Segment RT is congruent to WY, or ST is equal to WX, which the next step talks about RT equal to WY. So that would lead me to believe that segment RT being congruent to WY should be the first given there. And then what happens from here to here? We go from saying that the two segments are congruent to saying that their lengths are equal. So just like we ended that last one with, to switch between congruent and equal, and we're talking about segments, it's going to be the definition of congruent segments. All right, so then from there tells us that RT is equal to RS plus ST, and WY is equal to WX plus XY. So we're just identifying what RT and WY are made up of, because each one is made up of two segments. And that's a segment addition postulate. Anytime we say that one segment's made up of smaller segments added together. Now, since RT is equal to WY and RT is equal to RS plus ST, WY is equal to WX plus XY, then we use a substitution property to replace RT with RS plus ST. WY gets replaced with WX plus XY. So that was a substitution property of equality. Now, step 5, ST equals WX, which is hard to see where it comes from here, and that's because it doesn't come from the steps above it. It comes from up here where it gave it to us in the beginning of the proof. So that is given. And then segment RS equals segment XY, RS equals XY. So ST and WX disappeared from here. And we can do that because ST and WX, once we've said they're the same, if we subtract both of them from each side, then we're subtracting the same thing, right? Which is the subtraction property of equality. And then lastly, we need to end with RS, or segment RS is congruent to segment XY. We're saying they're equal. So we're going to end this kind of just like we started. We're switching from equal to congruent. Segment RS is congruent to segment XY, and that's the definition of congruent segments. All right, so one last one here. Given X is the midpoint of segment MN, and the length of MX equals the length of RX, prove that XN is equal to RX. Ultimately, we want to prove that from X to N is the same as from R to X, or X to R. So, starting off with what's given to us, or at least part of what's given to us, if they give us multiple parts. So, X is the midpoint of MN, and that is given. So now that we know that X is the midpoint, one thing we have to remember is what is a midpoint. And for a segment, the midpoint is the point that would divide the segment into two congruent segments. So that means that if X is the midpoint, then from m to x would be the same length as x to n. Mx equals xn. Definition midpoint. And so they're taking the information they gave us about the midpoint and basically came up with all the information we could from that. Since it's the midpoint, those two segments are equal. We got another part of the given though we can bring in to try to start another strand of statements. So mx equals rx. The reason for that is that it is given. And then when we look at this, we got mx is equal to xn and mx is equal to rx. Right, so we're trying to prove that xn is equal to rx. What we see is that xn and rx are both equal to the same thing. They're both equal to mx. So when they're equal to the same thing, they're supposed to be equal to each other, right? So that is xn equals rx. And the rule we use when we're saying that two things equal the same thing so they equal each other, it's called the transitive property. And we've got equal signs there, so of equality. Alright, so that completes that one. And hopefully you're starting to get kind of a idea or a sense of how we go through the process of doing a two-column proof. And that completes section